we're now going to start explaining the aim constraint. Before we explain the aim constraint, there are a few concepts we need to understand. First, in the 3D world, our coordinate system, we're all certainly very familiar with it by now. We know it's composed of an x-axis, a y-axis, and a z-axis. These three axes must always be perpendicular to each other. Another point is their positional relationship to each other is fixed. For example, if we determine the direction of the x-axis, and then we determine the direction of the y-axis, because their relationship to each other is fixed, our z-axis must be pointing in this direction. It can't be pointing in the opposite direction. That's impossible. This is a fixed rule of the 3D world. So when we rotate an object, what are we actually doing? What we're actually doing is constantly changing the directions of our three axes. And that's what ultimately creates the x, y, and z rotation values we see. We can also see this if we go into Maya. For example, I have a coordinate system model here. Watch as I rotate it. Let's not worry about the actual x, y, z rotation values. But we can see what's actually happening here is a change in the direction of the x, y, and z axis. No matter how I rotate it, it's always changing the direction of these three axes. And once I've settled on direction, for example right here, the directions of all three axes are now fixed. Maya can then, behind the scenes, through calculations, translate that into the corresponding x, y, z values we see in the channel box. So with that understanding, let's start looking at our aim constraint. We've mentioned the behavior of an aim constraint before. Essentially, it's our driven object rotating to always point at our driver object. So let's quickly draw this out. We'll use a light blue X to represent the driver object and a pink dot to represent the driven object. As we just said, an aim constraint is the effect of the driven object always pointing at the driver. So we'll draw an arrow. This brings us to the first concept, the aim vector. What is an aim vector? It's the axis points at our driver object. We know that in Maya, for something like translate, it has three attributes, x, y, and z. When we want to represent a vector, we also use the x, y, and z axis to represent it. Using Maya's default x-axis as an example, the representation here would be 1, 0, 0. If it's the y-axis, it's 0, 1, 0. The z-axis is 0, 0, 1. And if we want to represent the opposite direction of the x-axis, the minus x-axis, we can also represent that. That would be negative 1, 0, 0. The minus y-axis would be 0, negative 1, 0, and the minus z-axis is 0, 0, negative 1. We can also use, let's say, the direction between the x and y-axis to point at our driver object. For example, we could write 1, 1, 0. Maya supports this too, but from practical work experience, I've never encountered a situation that required this kind of setup. So let's keep it simple. Just stick to x, y, z, minus x, minus y, and minus z, and we'll get the best results. Okay, let's keep going. When we have the direction of one axis figured out, it can by itself help us directly figure out the corresponding rotation values for all three axes. Why is that? It's because our other two axes can still rotate infinitely around that one axis we've defined. There's an infinite number of possibilities. For example, let's jump into Maya and see. We can see my x-axis is now pointing in this direction. But I can still rotate along the x-axis, while keeping the x-axis direction unchanged, constantly change the other two axes directions. This is also why we can't get the final xyz values from just one single axis direction. So we need to go one step further and define the direction of a second axis. Because their positional relationship is fixed, and they are all perpendicular to each other. Once we define the direction of that second axis, the third axis direction is automatically figured out. So here we need and only need to define the direction of the second axis. This is where we need to introduce some new concepts. First is the up vector. This is the direction of that second axis we were just talking about. Maya defaults to using the y-axis 0, 1, 0. So how do we define the direction of this second axis? Maya gives us a few options for this. This attribute is called word up type. Maya provides us with some different choices here. Things like vector, scene up, object up, object rotation up, and none. Each one corresponds to a different method. Let's briefly explain them. First, let's talk about the simplest one, scene up. So we know that in our 3D world scene, what is the up direction? It's just our world y-axis direction. So here, we can set our second axis, which is our up vector, Maya defaults to y-axis, to be aligned with the world's up direction. So that's this direction. Correspondingly, since we know these two axes, we can get the direction of the third axis, z. This way, we've defined all three axes, and we can get our corresponding xyz rotation values. So this is what we call scene up. Next, let's talk about vector. This is basically we provide a vector direction. So for example, if we provide 0, 1, 0, then it's no different from the scene up we just talked about. But of course, we can change it. Let's say we change it to the x-axis 1, 0, 0. This is based on the scene. So the scene's x-axis direction is this way. Correspondingly, our y-axis is now this direction. And our z-axis would be pointing up. In this way, we can also get a corresponding rotation value. However, in rigging, we almost never use these two options. Why? Because in rigging, we generally don't use the world position as a reference. This is actually pretty easy to understand. For example, let's say we're rigging a character. This character in the 3D world. They could be moving around like we do in normal life, head up and feet down. But they might also encounter situations that are different from normal life. For example, maybe our character needs to do a flip, or they need to do a handstand. In those cases, we would become head down and feet up. If all the aim constraints we create in our rig are always using the words up as a reference, then when we're doing an action like a handstand, a lot of our rotations won't give us the behavior we want. So we need to remember, unless there's a special situation or a special reason, we basically never use the vector or scene up options. So next, let's focus on object up and object rotation up, because these two are actually the most commonly used settings when we're rigging. First, let's talk about object up. What is object up? Let's first recall how we defined our aim vector. How did we define it? It was very simple. We knew the positions of our driver and driven objects, so we drew a line between these 2 points. The direction of this line is the direction our aim vector represents. Object up is actually the same process. We find the point. This point is our up object. Then we draw a line between the up object and the driven object. This line represents the direction of our up vector. This way, we've defined the direction of our up axis. And similarly, we know the x and y axis, so correspondingly, we know where the z axis is. That is object up. Now, object rotation up might sound a bit harder to understand. It's actually very simple. We still find a reference object, but this time we no longer reference the object's position. Object up references the object's position, and we use those two positions to get the direction. But now we have a reference object, and this object can have any rotation. We specify axis direction from this reference object. For example, we'll use our reference objects. Let's just use the default xyz, so we'll take the reference object's y-axis. Correspondingly, our up vector will also match this direction. So similarly, we have two directions, and we can definitely get the direction of the third axis, and then determine our rotation values. This is the difference between object up and object rotation up. None actually uses a quaternion method to determine its up vector direction. As for the specifics of these, when we go back into 3D, we can do some comparisons and take a look at their similarities and differences.